Okay, class, we are looking at Lagrange multipliers. We already saw one nice example, and now we're going to look at another example. Okay, a little more complicated. Let me give you a moment to copy this example down. Okay, so in this problem, we want to find the minimum distance from a point on this nonlinear surface to the origin. And I want to mention something here. So in your homework, okay, let me just do something here. Okay, in your homework, you're going to have a variety of problems dealing with Lagrange multipliers. And if you had, for instance, a plane, if you had a plane and you had a point not on the plane, okay, I want to say this the right way. If you had a point outside the plane and you wanted to find the minimum distance between the point and the plane, of course, the constraint is that, let me just see here. I want to just phrase this the right way. Hold on here. Yeah, you'd have to find a point in the plane that's closest to the point outside the plane, the shortest distance. Okay, so in other words, what I'm trying to say is that if your surface were a plane and you wanted to find the minimum distance between a point outside the plane, I want to say it the right way. If you wanted to find the minimum distance between a plane and a point outside the plane, you'd have to find the point on the plane such that the distance is minimum. So that the distance is minimum. And there would only be one point. That point would be 1. But if you have a situation where you have some kind of, nonlinear surface, and you have a point, maybe a surface that kind of doubles back on itself, you could potentially have more than one point on the surface where the distance is minimized. There could be multiple points. And that's a situation, and you have to allow for that. That's the situation that we're dealing with here. So what we're trying to do is we're trying to minimize the distance. So the distance function is what you're trying to minimize. Okay. From a point, from the origin to a point on the surface. So in other words, the restriction is that the points that you're looking for have to be on the surface. So let's go ahead and look how we do this problem. So first of all, we want to minimize the distance, okay, between the origin, and I'm going to turn that off if I don't want to get emails here. I don't want that, you know. Here's the origin, and here are two potential points on the surface with coordinates x, y, z, okay? We want to minimize the distance, okay, between those points on the surface and the origin. But instead of minimizing the distance, we're going to minimize the square of the distance. In other words, our function that we wish to minimize is going to be the square of the distance. Because if we try to minimize the distance, because there's a square root in there, that makes life complicated. So instead, let's find the points on the surface that minimize the square of the distance, and that's equivalent to minimizing the distance itself. So we want to find the points on the surface that minimize the distance. We want to minimize the distance. We want to find points whose distance from the origin is minimized, subject to the constraint that x times y plus 2xc equals 5 root 5. In other words, this means that the coordinates x, y, z, those points, are on the surface. Okay, the points are on the surface. If you're requiring x, y, z to satisfy this constraint, if you're then any x, y, z, any point with coordinates x, y, z that satisfies that constraint means that that point is on the surface. So we are trying to find points on the surface that are closest to the origin. So we are minimizing the square of the distance between points on the surface to the origin. So of course what we have to do is set up our Lagrangian equations. So the gradient of f is just the vector with components 2x, 2y, and 2z. And the gradient for g, so the constraint is g of x, y, z equals 5 root 5. The gradient there has components y plus 2z, x, and 2x. Please let me know if you have any questions. Okay, please let me know. All right, so now we want to set up our Lagrangian equations. So here we have them set up on this page. And there is information here that is not necessary. I'm going to cross it out. Okay, there's some information here that is not really necessary, so I'm just crossing this out here. You don't need to copy that. I want to keep things simple here, okay? I want to keep things simple. So, okay. The components of the vectors, let me just perhaps put this below. Hold on here. Okay, I'm just sort of writing it out a little bit for you. So you have a vector on the left equaling lambda times a vector on the right. You equate the components, and you're going to get these three equations. You're going to get these three equations. Okay. Now, let me just see here. One moment. And let me put the constraint down too. Let me put that down here. The constraint, we mustn't forget that. That's x times y plus 2 times xz equals root 5. That's the constraint. How many unknowns are there with equations 1, 2, 3, and 4? How many? I'm sorry, I have an error here. This should be 5 root 5. So, based on these four equations, how many unknowns are there? 3 or 4? What the heck? My gosh, I'm getting angry here with this pen. Hold on. 4. That's right. I'm about ready to break a pen in half. Hold on here. Just got to avoid a button here. Hold on. Gosh darn it. I know I can program the pen, and that's what I'm going to have to do this weekend. I'm going to have to do a little. I know you can program it so like there's like a little button on it where if you touch it, it won't do anything, and that's what I gotta figure out. Narina, you're right. There are four equations. Here's the fourth one. x times y plus 2 times xz equals 5 root 5. Now what we're going to do, I'm not saying this is the only way to do this, but looking at equations 1, 2, and 3, the second equation is certainly the nicest looking one. And so I'm going to solve that and say, okay, x equals 2y over lambda. And that's my equation 5. I always number these equations as I go. And we'll just note that lambda is not going to equal 0 in this case, okay? Lambda is not going to equal 0. Let me just see if that, I always like to kind of justify my comments. But if lambda, well, yeah, lambda is not going to equal 0, okay? Now, let's just sort of not worry about this information here, okay, and get down to, finding these coordinates, x, y, and z. So I have this equation 5, and I'm going to substitute it in equation 3. So equation 3 is here, 2 times z equals lambda times 2x. I'm going to take equation 5, and I'm going to substitute it in for x, okay, in equation 3. Okay, now I'm just trying this. Hopefully it'll work. When I do that, hold on here. I get this. And based off of this, I determine that z equals 2 times y. And I'm calling that equation 6. I'm calling that equation 6. Okay. Now, what equation haven't I utilized of these 4 equations above here? Of these 4 equations above here, I've utilized equation 2 and equation 3, but we've not utilized equation 1 yet. Remember, you have to utilize all the equations. So what would be logical is, being I know that x equals 2y over lambda, that's equation 5. Being I know x equals 2y over lambda, and being, that's equation 5, and being I know that z equals 2 times y, that's equation 6, why don't I substitute in equations 5 and 6 into equation 1, which we've not used yet? Okay, certainly we can do that. And I'm going to show that on the next page. May I go to the next page? Are we okay so far? Okay, Angela's good. Aura's good. Yeva's good. Okay. Okay, so we go to the next page, and we're substituting those equations, 5 and 6, in equation 1. So remember, just for reference, equation 5 was x equals 2y over lambda, and equation 6 was z equals 2y. So here is x, and here is z. Okay, because this was equation 1, right? So we hope good things are going to happen, and we end up getting that 4y over lambda equals lambda times 5y. Now again, here, this is just extraneous information here. I don't want to complicate this. If 4y over lambda, I mean, if we look at this, we have y times 4 over lambda. So what I'm doing is I'm saying, look at this equation. Y times 4 over lambda equals y times 5 lambda, right? That equation is the same as this equation. Well, this means then that 4 over lambda would have to equal 5 lambda. 4 over lambda would have to equal 5 lambda then. We don't have to divide by y or anything, and we don't want to divide by y. We don't want to divide by a variable unless we can establish that that variable is non-zero. And sometimes we do need to establish that, but we're keeping it simple here. So what I'm going to do is I'm going to solve for lambda. I'm going to solve for lambda. So 4 over lambda equals 5 times lambda. And this means 4 equals 5 times lambda squared. So I'm going to multiply through by lambda. Lambda is not equal to 0. And I'm going to get lambda equals plus or minus 2 over root 5. That's what I'm going to get. Lambda equals plus or minus 2 over root 5. Okay. Now I'm going to just hold on to that. I'm going to keep that. I'm going to hold on to that. So lambda could take on one, or it could take on either value. So that's interesting. Now what equation haven't we used yet of the 4 equations? We've used equations 1, 2, 3, 1, 2, and 3, but we've not used the constraint yet. We have not used the constraint yet. So as you recall, the constraint, hold on here. One moment, we've not used the constraint. So let's just sort of see where we're at here. So the constraint, this is now separate from this. The constraint was x times y plus 2 times xz equals 5 root 5. Okay, that was the constraint. And let's remember, that was equation 4. Equation 5 was x equals 2y over lambda. And equation 6 was that z equals 2 times y. What I can do is I can substitute in x and z into the constraint equation. And because I know what lambda can be, I can actually ultimately solve for these coordinates. Okay, so that's what we're going to do. That's what we're going to do. Are there any questions before I go to the next page? Okay. So the next page, like I said, I'm going to substitute in. I mean, I have to find my coordinates x, y, z. I have to find the points on that surface that are closest to the origin. To find the points, I need coordinates x, y, and z. So I'm substituting in 5 and 6 into the constraint equation. Once again, equation 5 was x equals 2y over lambda, and equation 6 was z equals 2 times y. And there's the z, and there's the x. And I go through the math here, and I end up getting that y squared equals 5 root 5 divided by 10 times lambda. But that's okay, because I know the possibilities for lambda. One of the possibilities is that lambda equals 2 over the square root of 5. That's one of the possibilities for lambda. So if I substitute lambda, if I substitute that value of lambda in that equation, okay, I'm going to get a 1. And so y squared equals 1, so y equals plus or minus 1. Now that I know what y is, I can figure out, now that I know y equals 1 or negative 1, I can figure out the corresponding points. So remember, x was equal to 2y divided by lambda, right? That was equation 5. X is 2y over lambda. So here, x equals 2y over lambda. So in the case where lambda equals 2 over root 5, we're going to get z, we're going to get x equals root 5, okay, because 2 divided by 2 root 5 is like 2 over 1 times root 5 over 2, right? And you get root 5. And then z is equal to 2 times y, you get 2. So one of the points is root 5, comma 1, comma 2. Now when y equals negative 1, you'll get another point, which is negative root 5, negative 1, negative 2. Absolutely amazing. Absolutely amazing, really. Please let me know if you have any questions. So this is one of the harder ones. I wanted to do a hard one. I know you have one in your assignment that's interesting, put it that way. And the book has good examples, and there are a lot of help aids in the homework, but one of the problems doesn't have a help aid, and it's a little complicated. So I just wanted to provide an example to show you what's possible. I look at Lagrange multipliers, this approach. I look at it like wrestling. I don't know if you've ever seen like worldwide wrestling, but in the match, to win the match, how many have seen like in the matches they do crazy things to win? How many have watched wrestling and seen that? Like WWE wrestling. I don't know. I heard it's kind of popular. Okay, IB knows what I'm talking about. The point is, they do what they do. They try to do whatever they need to do to win the match. And so you're trying whatever you can do based on your equations. You're trying to come up with whatever you can come up with to eventually get the answer. And this works. Now remember, lambda was equal to 2 over root 5, but also you had a possibility that lambda could equal negative 2 over root 5. Well, if lambda equaled negative 2 over root 5, what would happen there? If you try that, if you try negative 2 over root 5, you'll get y squared. So remember what y squared was. Y squared, remember, we established that that y squared was equal to 5 root 5 over 10 times lambda, right? So if we put in lambda equals negative 2 over root 5, we'll get y squared equals negative 1, but then y would equal plus or minus I, and we get no real solution. So that was a dead end. That was a dead end. Because it's this surface is in our surface given by the equation x times y plus 2 times x times z equals 5 root 5. That surface is in three-dimensional space, and the coordinates on that surface that are closest to the origin would have real values. So, this isn't going to happen in this case. So it turns out there are only 2 values that work here, 2 coordinates, root 5, 1, 2, and negative root 5, negative 1, negative 2. Those are the points on the surface closest to the origin, and distance is root 10. Now, how do I know that? Well, I'll tell you what. Let me do it for the one of them here. So distance between the origin and let's say this point here, that point there. So this is going to give you 5 plus 1 plus 4, and that's how you get root 10. And if you put in the other value as well into the distance formula, you'll also get root 10. So that's how it works. Incredibly important concept, Lagrange multipliers. They come up. I know I've seen them, for instance, used in economic, like papers on economics, for instance, and they come up in statistics as well. So it's they're important in math. A lot of applications. And Lagrange multipliers, you can even come up with they have, like, for instance, what if you wanted to maximize or minimize a surface or a function subject to two constraints, not one constraint, but two constraints? Well, they talk about that in the book and give an example, example 5, and then there's formula 16. But we're just going to stick to one constraint for our class because these problems can get incredibly complicated. Okay, and I just want you to be able to, you know, this is just an introduction, basically, into this. Are there any questions before I stop the recording? How many of you think this is kind of cool, what you're learning here? Okay, Aura's liking it. Good, good. And Norina is, and hopefully the homework problems should be pretty, a lot of times, okay, so what, how do we find our values, right? What paths do we use? Hopefully the path should be hopefully the process should be fairly straightforward and obvious, or at least fairly straightforward. It might take a little thought. But they're like little puzzles when you solve these kind of problems. There's little puzzles, and sometimes people can get to the answer in different ways. But usually, usually there's a sort of a clear way to getting the answer. The book has a nice example also, example 4, that you might want to look at as well. Okay, if there are no questions, I will stop the recording. Okay, very good, very good.